which is holomorphic, and I have that f of 0 is equal to 0. And under these circumstances, I can define a function g going from d2 0 to c a priori, given by g of z is equal to f of z divided by z if z is different from 0, and is equal to f prime of z if z is equal to 0. And this is a holomorphic function on d2 0. Now I note that if we have that g of z is less than or equal to 1 over norm z for all z. Okay, and in particular, we have that g of z is less than 1 over 1 minus epsilon on the boundary delta of the disk of a radius 1 minus epsilon. Okay, so by the maximum principle, this gives me that g of z, absolute value, is less than or equal to 1 minus epsilon for all positive epsilon. So in particular, absolute value of g of 0 is less than or equal to, 1 over 1 minus epsilon, less than or equal to 1, and that gives me the absolute value of f prime of 0 is less than or equal to 1, and in particular, if f from d0 to d0 is a biholomorphism fixing 0, then I have both that f prime of 0, absolute value is less than or equal to 1, and f minus 1, derivative of 0 is less than or equal to minus 1, which gives me that f prime of 0 is equal to 1. Okay, now, suppose I have that f which goes from the Poincare disk to itself is not supposed to fix 0, but is a biholomorphism. Okay? I'm going to show this in a hyperbolic isometry. Now, I'm going to take an arbitrary point P in d2 0, and I'm going to set Q to be f of P. Now I'm going to let G1 and G2 be Möbius transforms of the disk, fixing the disk such that G1 of 0 is equal to P and G2 of Q is equal to 0, such that if I look at G1 F G2 is a biholomorphism of the Poincare disk fixing 0. Okay? So we have that G2F G1 going from the tangent space at 0 of the Poincare disk to itself. So I'm just looking at the effect this has on the tangent space at 0 is a hyperbolic isometry, i.e. it respects the scalar products on these two tangent spaces that gives rise to the hyperbolic metric, but we were assuming that Möbius transforms are known to be hyperbolic isometries, so G1 and G2 are hyperbolic isometries. So since G1 and G2, maybe I should call this the derivative at 0, are hyperbolic isometries, what I get is that the derivative of f going from the tangent space at P to the tangent space at Q is a hyperbolic isometry. Okay, and now what I've got left is to show that that the only biholomorphisms are the Möbius transformations. So what I'm going to do now is suppose that I have f going from D2 to D2, 0, a hyperbolic isometry. Okay, let me say, more to the point, I'm going to ask that it should be a biholomorphism. Sorry. So I'm assuming it's a biholomorphism. Okay, suppose it fixes 2 points, P and Q, disjoint. And now I know that f is an isometry, and therefore it's going to fix this f, must fix the whole geodesic between P and Q. Pointwise. F fixes geodesic from P to Q pointwise. Okay, and then we have a hyperbolic, it's a biholomorphism that fixes a whole line, and so f fixes a line. So by a hyperbolic line, so by the zero principle, f is the identity. Okay, so now what I want to prove is that any automorphism of D2, 0 is any biholomorphism of D2, 0 is actually a Möbius transform. So suppose that f going from D2, 0 to D2, 0 is a biholomorphism, and I'm going to take 2 points, Z1 and Z2 in D2, 0, which can be anything, they just have to be different. I'm going to say that f of Z1 is equal to omega 1 and f of Z2 is equal to omega 2. Now I pick G, a Möbius transform, such that G of W1 is equal to Z1 and G of W2 is equal to Z2. And this will give me that G times F is an automorphism fixing 2 points, Z1 and Z2, which gives me that F is G minus 1. The inverse of a Möbius transform is a Möbius transform. So that's all done.